Hello everyone, thanks for coming. My name is Matějek. I work for the Trezor company and I will be talking about how to integrate MicroPython and Rust and what are some problems encountered there. First of all, let me tell you about what I do and why I'm even solving this problem. This is the Trezor T. It's a couple years old now. It's a hardware cryptocurrency wallet. So basically a security token that manages your money. So there's actually a built-in bug bounty. If you find an exploit for this device, you can just directly take money from people's wallets. So that means that we really need to be very careful about security. We cannot fix vulnerable code, ship it later. It's completely open source, and it runs, this old model runs on the STM32F4. Newer models run on the newer U5, but it's not much better. And this has 2 megabytes of flash and 192 kilobytes of RAM, which is not a lot. And most of the firmware is written in MicroPython. It's pretty large for a MicroPython project. It's like 65,000 lines of code. I don't think anyone ever envisioned using MicroPython for something this big. And we originally intended this to be completely written in MicroPython, except the super low-level functions that initialize it and some drivers maybe. Never achieved that, and it's probably a good thing. It's not super practical to do it this way. Unfortunately, MicroPython is a dynamic language, and that means that it has some drawbacks, and at this size, these become significant. So first of all, every import, when you write from something import, takes up space in RAM because the dictionary needs to be dynamic, it needs to be modifiable, and so it's loaded into RAM, and we don't have a lot of that. A lot of operations allocate memory. Like, for instance, if you do a string slice, that's a copy of the string. If you append to a list, of course, that can allocate. And funnily enough, if you make a number that's large enough, that also allocates. So just multiplication, increment by 1, all new allocation. And due to how the memory management is implemented, the less available RAM you have remaining for allocation, the slower it gets. So we need to get some speed here. So there's our problem statement. We have a microcontroller. Let's say it has 265 kilobytes. We have a huge legacy base of MicroPython code. We need to write more, but we need to be faster because MicroPython is relatively slow all by itself, and we need it to consume less RAM. Now, there's an easy industry-grade answer to that, which is C, of course. Unfortunately, it must be memory safe as well, so C is out of the question. Remember, we chose MicroPython because the product is security critical, and MicroPython is a memory safe language, hopefully as long as the interpreter is written right. But yeah, it hasn't been a problem so far. So let's go Rust. And now we have 2 problems. You're here on the last talk of the Rust track, so-called, so you probably all know this, but let's go over it because I will be referring to it again and again. First, a refresher. A computer memory is just a huge array of bytes. You can interpret them as data structures, and pointers are just indexes into the array. So building memory safety on top of a computer is difficult. Like, anyone can write anything, read anything, no guarantee that pointer points to the start of anything, etc., etc. So what Rust does is introduce abstractions and one very important concept, and that is ownership. Every value has exactly one owner who can do anything with it, mutate it, read it, write it. And if you want to change owner, you move the value, but that means that the previous owner can't touch it anymore, right? And the owner can loan out the value, give out borrows, and in that case, the value still belongs to the owner, but he can't use it until the borrow is returned. Back to pointers, Rust doesn't let you use raw pointers, safe Rust anyway, so we are using references, and reference is just a fancy pointer that is guaranteed to always point to valid data. There are two kinds of borrows, you also know this. Immutable and shared borrow, when everyone can look but nobody can touch, and mutable or exclusive borrow, which means that who has it can touch it, but nobody else can look. Why not? Because that's how you get data races. If you see modification in the middle, you see something wrong. So just to quickly summarize, every value has exactly one owner who is responsible for allocating and deallocating. Pointer can be either shared but immutable, or exclusive and mutable. Now let's look on the Python side of things. Unlike some low-level languages, Python doesn't really concern itself with how computer memory actually looks. Everything in Python is an abstract object. An object is basically a namespace, it has attributes, and those attributes are bindings to objects. No primitive types, no pointers, they're just links to other objects in the abstract object space. For instance, the number, oh dear, this is very low contrast. Oh my. I forgot to check my color scheme wonder. Can you all read it okay? Or should I? Yeah, okay. Let's hope it works fine. Can we maybe change something about the projector? Yeah, okay. I'm sorry about that. Let's continue. So the number 42 is an object. It's a namespace, it has attributes. The attributes are immutable, but they are there. And the function itself is also a namespace. It's not technically an object. And we are, of course, allowed to bind to the same object multiple times. Here's a schematic, and you see that the data and the local objects are pointed to from multiple places. We can, of course, have cycles pointing back to itself. You can even point from the same object to the same object. You're always pointing to an object, not to an attribute, so it's just like this. But as we've seen before, computer memory does not look like this, so how do we implement it? We start by designating an area of memory for the object arena, or GC arena, from which every object will be allocated. We reserve a small chunk of this memory to be an allocation map. There's metadata about what is allocated and what isn't. And then every time we need to create a new object, we allocate a chunk of this memory from this arena and get back a pointer to a beginning of this allocation, or so-called head pointer. And then we can store this pointer and use it to refer to the object. In C terms, we have this special type MP object T, and it always must point to a head of the allocation. And then every attribute of every object is just this type, this pointer. The allocations are always aligned on 32-bit platforms to 16 bytes. So every allocation size must be a multiple of 16 bytes. And that means that every valid pointer has some zeros at the end. That's free real estate. So let's use it, right? We use a technique called pointer tagging to store some data in the pointer if it's not a pointer. For instance, if the last bit is 1, then the first 31 are an integer, small integer that fits into 31 bits. If it is bigger, then we need to allocate it as a separate object. Ints are immutable, so it doesn't matter that these are not real objects. Similarly, if the pattern at the end is 0, 1, 0, it's an ID of an intern string, or so-called Q string. If it's 1, 1, 0, it's a special value. There's actually only like 6 of those special values, but we have 29 bits for them. And finally, in the last case, if there are zeros at the end, it's an actual pointer. And if that happens, then MicroPython follows that pointer and expects that the first item that it finds is a type pointer, which is a pointer to a different object. This is an example. It's a representation of a Python list. This is the type pointer. Then we have some allocation, the actual length, and then we have an array of items, each of which is, again, an object pointer. Note that this is actually a pointer to an array of pointers, but this is not an object itself. This actually points to an allocation, but that allocation does not have base as its first item. It's just a list of objects that are contents. You can also note that these are exactly 4 items. On a 32-bit platform, that's 4 bytes each, and that's 16 bytes total. So this thing takes up exactly 1 allocation, which is nice because you don't need 2. And this is how the type object looks like. First of all, types in Python are also objects. So this is also an object, has a base as its first item, has some flags, has a name. The name is not a string, it's an int. It's one of those intern values. And these are function types that implement some features of the objects that MicroPython supports. You have binary operators, unary operators, attribute access, subscript, etc. Lots of them. Now let's talk deallocation. We don't have unlimited RAM, unfortunately, so we have to deallocate. But how do we do it? Like, if I deallocate something, and someone is still pointing to it, what now? Meet this guy. His name is Mark. What he does is sweep, and he's a garbage collector. In CPython that runs on your big PC, they use reference counting. Every operation increments a reference count and decrement it. MicroPython does not do this. We have mark and sweep garbage collector. We start with a set of root pointers that are predefined. Look at the first one, mark it as visited in the allocation map. And then we go through whole allocation belonging to that pointer and look for things that look like pointers. We can recognize pointers because they are 4 bytes. They must point into the arena, which is limited, and they must have ending zeros, so we can find them. Of course, sometimes we find things that are not pointers. That's unfortunate. And every time we find something, we also mark it, add it to the set, and continue. And then finally, when this is all done, we have no more pointers remaining. We walk the allocation map, and if something is not visited, then we deallocate it, and that's done. So to summarize, every variable or attribute is actually implemented as a pointer to a start of an allocated area. Everyone can store this pointer wherever they like, make copies, etc. And only when nothing points to that area anymore, it is deallocated after the GC is called. So now these two worlds should meet. Rust says there's only one owner. Python says anyone has a pointer. Rust says you can have shared and immutable pointers. Python says anyone has a pointer. Rust says if you're mutable, you're exclusive, but Python says anyone has a pointer. So that's a problem. Or is it? I mean, is this little girl right? Could we do both at the same time? Like, technically, we could split the memory in half or some other ratio, mark one area for MicroPython, the other area for Rust, and each does its own thing. Memory models don't cross. I mean, we could do it, probably, but maybe not. So first of all, we don't really have enough RAM for that. We have 256 kilobytes. Even if we split it in half, means each language gets at most 128, which may be less than we need. And we need to decide whether this place should be in Rust, this place should be in MicroPython. It's bringing all sorts of ugly difficulties. That's not the only problem. If Rust points to a Python object, then the GC suddenly doesn't know that there's a pointer to it. So it can silently deallocate and invalidate the pointer. This is solvable. We could implement a new GC route and put pointers into it, and on the Rust side use something like RC to ref count them and then remove them when the wrapper is dropped, etc. But it's a lot of work. And of course, another problem is the other way. When Python points to Rust, then Rust allocator never knows if something is deallocated. So slowly we will leak memory and fill up the section reserved for Rust. This is kind of solvable too. There's a support for finalizers in the garbage collector, and we could set a finalizer and indicate to Rust that it should deallocate. But again, it's a lot of work, and still we don't have enough RAM. And remember, the original problem statement says that we are extending MicroPython. So making a separate Rust memory is not really in that spirit. It might bring problems. So let's not do that. Without further ado, let's look what we are actually doing. Very first thing we need to do is make an object type. We call it obj to represent the MP object T. And in Rust, this type alias allows us, well, we could do it without it, but it's a nicer name. And we implement some functions on it. Most of them are identifying what the object is and conversions from and to different kinds of Rust objects. For instance, ints. There's a pretty rich API in C for MicroPython that has a lot of functions to work with Python values. For instance, MP object getInt maybe, which will return the integer as a C value or throw an exception. On the Rust side, we have standard from and try from types that give us idiomatic conversions. There's a catch exception function. I will talk about it later. Let's put a pin on it for now. Otherwise, it's pretty straightforward. I make a result, call an unsafe function from the C API. If I got something, I return an OK. Otherwise, I return an error. Because the failure that could have happened here is that I'm trying to get an int from something that's not an int, so it's a type error. Creating a Python int from a Rust int is also straightforward. For small ints, we just create them directly. Remember how I talked about pointer tagging. So this is how I set a 16-bit value that always fits into 32 bits. If it's bigger, I have to do something a little more complicated, that is calling into the C API. Again, I'm implementing try from for object and calling function MP object new int, which may or may not allocate. So that's a reason that an exception could be raised here. So we're catching it, but there's not much more to it. Booleans are pretty easy too. It's even a little bit easier because true and false are constants, so we just return one or the other. The other way is a little more complicated because when converting from Python, we're not supposed to look for the constants themselves, but look whether the value is truthy or falsy. So for that, we have a function MP object is true that returns true false, and that's basically it. We still, again, have a risk of an exception here, especially when someone is implementing a custom dunder bool method in Python that may be buggy, may have some exception. So it can happen that an exception is raised here. Let's look at true objects, which can be anything else. These were just simple values, basically primitive types. The way we look at an object is through the MP object T, which is a pointer. And Rust recognizes pointers, raw pointers. Safe Rust doesn't let you do anything with them, but you can use them. And the owner of a pointer is, well, nobody, or maybe technically the garbage collector. We cannot safely dereference them, we can borrow them because we have no exclusivity guarantee, we have no immutability guarantee, so that's unpleasant. What we do to hide this from Rust, we implement a wrapper pointer type, it's called GC for garbage collector, and it allows you to, in this case, unsafely get a mutable or immutable reference. And ensuring the safety of those operations is up to the caller. They must make sure that what they're doing is okay. And that's not super great. What's the worst that could happen, you ask? Well, first of all, the programmer could be careless, store multiple mutable references to the same value. They might even do it by mistake. If you have a function exposed to Python, accepts 2 buffer arguments, and the caller passes in the same buffer. So on the Rust side, I could do smooth on both, and that's instant undefined behavior, right? So that's a problem. And another problem could be caused by Python. If I'm holding a value, it's a shared immutable reference, and Python decides to mutate it. That's also instant undefined behavior. So that's a problem. In normal big standard Rust with allocations, we have this nice man. You allocate something, you put it into a box. And the box is an owned type, so the owner is responsible for allocating, deallocating. If it goes out of scope, it's deallocated, so that's useful. And we would like it here too. So what we do is do a GC box for garbage collected. So because a GC box can only be created from Rust, it's a wrapper type, we know for sure that no one else holds that pointer, so we are the sole owner under Rust rules. Means we can safely do sref, smute, because Rust's borrow checker will check the safety for us. And what's a nice plus, when a GC box goes out of scope, it's deallocated. But, okay, so we have a pointer. We know that we're the sole owner, but what if someone takes it away? How does it interact here? So as long as the garbage collector sees the pointer inside the GC, it won't deallocate it. There is a pretty important catch here, and it's a phrase, as long as the GC sees it. The garbage collector actually goes through the call stack, so if I have local variables, they will not get deallocated. But imagine that we ever put a GC box in a global variable. And we forget to do the whole song and dance about somehow telling Python that we're storing this here and marking as a GC root. So that's a pretty glaring soundness hole, because then the garbage collector can deallocate the value and the Rust is left with a dangling pointer. In full honesty, we don't actually care about this one too much, because first of all, putting things in globals is a lot of work in Rust, and second, we're not doing that. We're not putting things in globals ever, basically. So for our code base, this is unlikely to happen, but it is a problem. There is another smaller soundness hole here too. If someone deleted the whole MicroPython virtual machine, this would also mess up our data. In the typical case, this will not happen because you initialize the virtual machine at start of your program and shut it down with the end of your program, so this is not happening. Both of those can actually be solved the same way, and I will talk about that later. For now, let's look at strings. Strings are nice because on the Python side, strings are immutable to same as Rust. So that means that if I grab a reference to the string data, Python virtual machine promises to me that it will never mutate it. And it's safe to carry around the reference. Data of the string is just a car pointer, it's immutable. So this conversion can be made safe. But again, what about marked garbage collector? While we are holding the reference, again, somewhere the GC can see it, it won't be collected, so that's fine. There's the same problem as I shown before, but let's not bother ourselves too much with that. The problem appears when we do this. When we make a slice that points to the first character and drop the original reference, then suddenly substr is no longer a head pointer. It has a 1 bit at the end. So the garbage collector doesn't see it. It's not a pointer anymore. It's not a head pointer. So it's free to collect the original data, and that invalidates the string. So that's a problem. The solution to this problem is to make an owned wrapper type. It's called strbuffer for some historical reason, not sure why. It always stores the head pointer here, and stores the length and an offset so that we can slice the str buffer, we can drop characters from the beginning, from the end. What's nice about this is that this asref function is now safe. There is some safety considerations. We do a lot of checking up front when we construct it. So when we are trying to get the string reference out of the str buffer, we can just do the conversion here. And of course, the lifetime of this string is tied to the str buffer, which is owned. So as long as the program holds this, it holds the head pointer, and it's not going to get deallocated. So the string is safe to work with for as long as Rust allows it to run. Let's look at bytes. Bytes are a little more difficult because Python has 3 distinct byte-like types. First is bytes that are immutable. And here we could, in theory, do the same thing we're doing with strings. Unfortunately, we have also byte array, which is mutable, and a special thing called memory view. In embedded environment, we are using it quite a lot. And that's a view into someone else's data. Could be immutable, could be mutable. Definitely causes sharedness. So even if I took byte array mutably, then a memory view from outside could modify it. So that's unfortunate. We could limit our APIs to just bytes, but that's impractical. It turns out that in our program, we are using memory views a lot. Because if we didn't, we would be forcing the caller to do some useless conversions to bytes. And especially in the case of memory view, we are typically looking into big data, and copying around a couple kilobytes is painful. So we don't want to do that. And of course, we still have the problem of the function with 2 arguments, and both of them are the same buffer, or 2 functions in sequence when you get buffer 1, buffer 2, but you stored the previous one. So that's unfortunate, and as a result, we are unable to make a safe API in this case. We have this getBuffer function, which is unsafe. It has an unbounded lifetime and returns a slice of that lifetime. The unbounded lifetime means that it can be anything, so typically static. So the lifetime annotation is essentially a lie, and the caller must be super responsible about using it. Must not store the result longer than absolutely necessary. Ideally, you just grab the buffer, do something, and immediately release it. And you must be specifically careful about not calling into MicroPython while you're holding it, because MicroPython can do anything about your reference. So this is not a great interface. We have an idea about fixing it, but it's going to take some amount of work. Let's move on to other types of objects. Python has built-in lists, built-in dictionaries, built-in sets, etc. We implement a wrapper for every Python type that we use. That's basically list, dictionaries, iterators. And let's look at how that looks. Wait a minute. Yeah, here we go. So this is a map. That's an underlying storage for dicts, for objects, for modules. And we have some constructors, and then we have methods. And each of those methods inside basically calls into the API from C to perform the operation, then converts back the results to what we need. Here's a different example for a list, and this is our conversion function. First of all, we must check that the passed-in object is actually a list. There's an unsave here. That's basically a technicality, and it's because this MP type list is a constant coming from C. So in Rust, it's an extern static, and touching extern statics is always unsafe. Other than that, it's safe. It's actually safe in our case because we know for a fact that this value is stored in flash and is immutable. So this is just technicality. And if it is a list, we do this weird song and dance, basically converting the object into pointer and then unwrapping it as the GC and returning the result. In case it's not a list, it's a type error. As it turns out, While working on this task, I discovered another soundness hole in our code base. I previously talked about how GC function sref is unsafe because there are no guarantees about immutability of the underlying value. This is still true here. And we have all those methods on list, but we want to work on the GC wrapped version because we are always getting lists outside the Python's memory. So we have this unsafe sref, and for convenience, we implement also a deref trait, which means that I can dereference a GC list into a list. But unfortunately, while this allows us to conveniently call all the methods of list on the type GCT, it's also unsafe because this is equivalent to calling sref in result. But if you store this X, then you are breaking all these invariants. So this is something that I discovered recently. We need to fix it. I believe the solution is going to be implementing all the methods not on the list itself, but on the GC wrapped version. Because this can be done safely. In normal usage, this is perfectly fine, because what you do is take the reference, run a function on it, and then immediately discard the reference, and that's OK. The only problem is when someone stores it for later. So if I implement the methods on the GC wrapper, I can do the same pattern and encapsulate the unsafety. But it's not done yet, unfortunately. Let's talk error handling. We've seen some functions about catching exceptions. Python errors are typically propagated as exceptions. You raise in one place, you can catch it anywhere above it in the call stacks. In Rust, we do things differently. We have the result type, which is an enum between OK and the value, or an error and that value. Of course, we can also panic and then catch the panic and unwind, but that's thorny. We're not doing that. Instead, we're going to be converting between results and exceptions. Going from result to exception is pretty OK. We have a custom error enum that enumerates some possible errors. And we have this unsafe function that converts it into Python object. This is unsafe because creating an exception, this function is special. And MicroPython has something called the emergency exception buffer. So that's a little space reserved for exceptions, so that even if your memory is completely full, you can still allocate an out-of-memory exception or any other type of exception and raise it without calling the allocator and failing. So that means that there is one single space for all of those exceptions. And if you call this into object twice, it will override the previous result. So that's the reason this is unsafe. You need to do it carefully. Safety conditions here are you're basically supposed to immediately erase the result of this back into C and not touch it anymore. Raising an exception is fun. In MicroPython, exceptions are implemented as non-local returns, or NLRs. That's set jump and log jump on the x86 platform. And in Rust, doing this is super unsafe because it breaks the scope exit rules. Basically, if you non-local return from somewhere, nothing gets dropped, nothing gets finalized. And you're in completely inconsistent state. More importantly, last time I looked into this, which admittedly is a couple of years ago, using NLRs would miscompile. You would get something super weird. So we cannot do that. What we do instead is unsafely call into MicroPython's API, which has a handy function to do the NLR jump from C, where it compiles correctly. So we pass that error object into the jump. Let's see. We call this external function NLR jump and give it the error object we just created on the previous slide. And this function is declared no return. That's the bank character right there, indicating that it's never going to come back to Rust. And far as we know, the only safe place to do this is the exact moment before a function would return into C from the Rust call stack and leave Rust completely. So this is how it looks like this. We have function try or raise that accepts a closure. The closure returns a result, and what we do is call it, and if the result is error, we call raise exception, and that's it. That's the whole function, and this one must be called at the end of a function that is exposed to MicroPython. Catching an exception. Now we're getting back here to what I talked about before. The signature of this function, it's accepting a closure that returns just type t, and it returns a result over type, either the t that's originally coming from the closure or an exception that was caught. The closure is something that we accept can raise on Python side, and it should catch the exception. But how does it do that? Well, that's super fun and super weird. In Python, the exception natively have scopes. You have functions, call stack, whiles, tries, blah, blah. And any outer scope can catch any exception from any inner scope. In the C implementation, you have to do the scoping manually by registering NLR handlers. So there's a stack of those. And remember, we cannot do this from Rust because it would miscompile. Also because Rust would hate us. So again, we have to do this in C. There's the function NLR push, which is the destination for the NLR jump. And that holds until someone pushes a new one. And this is how a C function that we implemented to do this for us looks. Accepts two arguments, a function pointer and some sort of argument. Here we have done an NLR push. This is the non-local return target. If it's 0, we call the function and then pop ourselves. And if it returns anything else, that means that the non-local return has actually happened. It throws us back here. And we go to this else branch, and we are returning the return value that we got from the NLR jump, which is typically the exception. And this is the Rust side. I was forced to revisit this piece of code for this talk, and to be honest, I still don't fully understand it, but I'll show it to you nevertheless. So apparently, in Rust, if you have a pointer to a closure or a reference, it's actually a pointer to the data for that closure. So essentially, the piece of the scope that the closure is over. And what this function, split func into callback and argument, does is two things. First, there's this trampoline that monomorphizes over this particular closure. So trampoline f for some specific f is actually a normal function that you can point to. You cannot point to a closure, you can point to a function. And what it actually does is just call the closure, convert the argument, and call it. And the second thing it does, it converts the function reference, the reference to the closure, first into a pointer, and then into this thing which is a void pointer. So that's how we get the argument for the function. And then if you call trampoline and put this as its argument, it does the conversion in reverse, essentially. We cast the argument into a pointer of the closure type, and then we invoke the function. So with this, we can now split the closure into something we can pass into C, call back an argument. We invoke this function treasure object called protected that I showed you before. And if the return value is null, then that means that the closure has succeeded. And we return an OK, and otherwise we return the exception that was caught. Not shown here is how we get out the return value. And that's by wrapping the closure into another closure and storing its result. And we are using a maybe uninit value. It's this one. The result is originally maybe uninit. And if the exception is null, then we are sure that the function was completed and the result was filled correctly. Okay, this one was difficult. Let's look at how it's used. This is the example from before. We call catch exception. We give it an argument, a closure that's calling something that could raise. And the return value is just this result. It's pretty easy, pretty nice. Again, I discovered the soundless hole here. The catch exception function should be unsafe. And the reason for that is if you put something more complicated into this closure, for instance, creating some objects and then relying on them getting deinitialized, then you're breaking the Rust safety rules by skipping over the deinitialization. Fortunately, like 99% of our usages of catch exception look exactly like this. There is just one foreign function call, so they are okay, but we do need to mark them as unsafe for this reason. So that's the thing that I'm going to be doing when I come back from this conference. Let's briefly look at iterators. In Python, iterator is actually itself a kind of object. We can iterate over different things. Lists, strings, we have generator functions. So the iterator object is a state of the currently running iterator. It could be a pointer to a list. It could be a running state of the generator function. There's a generic C API for working with iterators, and it's based on the C passing in an iterbuff temporary object, which you typically allocate on stack. Just create a struct, push it into function mp_getIter, which initializes it. And the funny part is, why I'm talking about this, is that this function creates the iterator object and returns what Python would consider its iterator object, but it's literally this thing that you passed in the typical case. Like there are some specials, but typically it's just this. And then you have iter next that gives you either the next item or raises an exception. So to make this work in Rust, we create an iterbuff wrapper. I am not showing it here, so you're going to have to trust me. And it essentially stores, I don't know, there's some data. And oh yeah, no, sorry. I know why I'm not showing it here. It's actually type alias to the iterbuff structure from before. Yeah, that's the reason. Sorry. So this is an iter object that actually implements the iterator on the Rust side. And this is the return value from mp_getIter, which may or may not be the same thing as this iterbuff reference. Typically, it is the same thing, but it might not be. And this is just a marker to tell us whether we're finished there or not, because Python returns a special value when you call the iter next to indicate that iterating is over. And with this thing, we can iterate over an object. To make it more ergonomic, we have an encapsulation method. So we first, in order to iterate over this field, we need to create an iterbuff that has nothing to do with that field. Just create it, and then tell us, please, iterbuff, iterate over the value we just passed in. And of course, this iter value is of type object or object, so we need to convert it to what we actually want. Because, like for instance, in Rust, in Python, a list can contain anything, different types of values. Last thing I wanted to talk about, there's a safer approach to some of the problems that I've shown you before. What we actually should be doing is create some sort of reference to the interpreter itself. There are several options to that. That could be a global. Maybe a better choice is to somewhere in some layer create a new reference and then pass it to a closure. So every function that can be called from MicroPython into Rust will magically get an additional argument. And this argument will be required to call MicroPython APIs, either mutably or immutably. And this will have a lifetime, some sort of lifetime that you can replicate. And without this lock, you will not be able to touch anything. So, for instance, if I go back, to here, and specifically to here, GCBox would get a lifetime parameter called 'VM, and that would be bound to the lifetime of the interpreter. And this would mean that I can never store it in a global or anywhere outside the interpreter, because when my interpreter instance goes out of scope, this would be invalid, so Rust compiler wouldn't let me do it. So we haven't tried it yet. It's going to be some amount of work. We would basically need to pass the interpreter parameter through a lot of places. And our Rust code base is already pretty big, so it's going to take some amount of work. But I hear other people have tried it already. There's a Pyo3 project for CPython, and they are doing something similar. So we're going to be taking inspiration there. And that's it from me. Thank you for listening. Here's a code for the slides if you want it. And if you have any questions, feel free to ask. Yes?
I'll ask the obvious question maybe. Why are you still using Python? At some point, like you said, you have a fair amount of MicroPython code here, but there is a lot of complexity in the translation.
True, yeah.
Systems. At what point is it better to simply rewrite the MicroPython to Rust and have everything running in Rust?
Yeah, so we're not there yet. That's the main answer. Some of our MicroPython code is quite complicated. For instance, Bitcoin signing. I'm not sure if you're familiar with Bitcoin formats, Bitcoin transactions, but we're solving a very separate difficult problem, and that is how to stream a huge Bitcoin transaction into limited memory. And we have this custom protocol that does all this hashing and double checking, because you need to stream some parts multiple times and verify that these are the same parts that you saw before. And this is a lot of complexity, and you don't want to be touching that without a very good reason. That's one thing. Another thing is that MicroPython is pretty high level, and it's actually much nicer to work in, especially when we are planning to open up development of different cryptocurrency apps to outside. So we would like them to be able to just use the Python. This is actually a very new project for us, and we might be able to get rid of a lot of complexity here by severely limiting what the Python code can do. Right now, with the big code base, you need to work with the MicroPython on most things, but we will be reducing those places and reducing the size of the interface. So yeah, I mean, you're right, kind of. And the third reason here, that's strange, but it's true. The fact that Python is higher level means that very often the code written in MicroPython and compiled into bytecode is smaller than the equivalent code for Rust. Because basically you're doing the same amount of work in fewer instructions, that's it. Like a thing we're running into a lot is that in Rust we need generic code with some type parameters, and this gets monomorphized. So we have 5 implementations of essentially the same code, but on a different type. Whereas in Python, you just write the one implementation, it just works on all types. So, yeah.
But would that monomorization be needed if you didn't have to interface with MicroPython?
For the things that we're using it for, that's mainly in the UI subsystem, yes. Oh, right, yeah. So the test bed for the reimplementation was Protobuf codec. We did have a custom protobuf implementation in Python. We rewrote that into Rust. We gained like 5 times speed up, so that's awesome. And the second part is super unsuitable for Rust, and it's the UI toolkit. Unfortunately, we need speed there, so because like drawing on screen, fluidity, etc. So we wrote a completely custom Rust embedded toolkit for UI. And unfortunately, it's so custom that we cannot package it and give it to someone else because it really doesn't make sense in its current state anyway. So that's fun. That's actually most of the code base. We are adding more things. For instance, now that we have nice macros for generating bindings from Rust to MicroPython, we are using that instead of C. Like previously, we would write, if we need to expose functions of drivers, we would write that in C. Now we're writing that in Rust. There's a part that we are not rewriting into Rust that's actually C, and that's all the cryptography. Signatures, hashes. The reason for that is that writing cryptography in Rust is painful. Like you have no control over how the memory gets moved, so you have to use pins. And I'm not super sure what's going on under the hood anyway. And we have this nice solid cryptography library with different side channels covered, and it's partially fuzzed, so we don't want to mess with that. Yeah, but we are slowly moving to like rewriting kind of the platform into Rust so that the event loop runs in Rust, some communication protocols runs in Rust, and the only thing that actually need Python are the applications themselves. And when we manage that, what we intend to do is move control over the MicroPython interpreter into Rust, so that when you start an application, you spin up a completely new VM, run the Python, then shut it down. And there we will need this thing that I talked about previously, this reference to the interpreter, because we will be actually in control of it. Yes?
Taking inspiration from Python 3, I presume that you have to constrain to Rust Python because most of the things that you have been doing here are supposed to be implemented at a certain level. Have you also getting some inspiration from one of the many Rust implementations of the Python interpreter, or
Oh.
decided to go?
I'm sorry, you're the first person that I hear mentioning this, so that never even occurred to me.
Yeah, Rust Python, I think, is the more advanced one, since they managed to get a large portion of standard library. But interestingly, in 2021 or 2, I think that they add support to cross-compile it for a few microcontrollers.
Mm-hmm.
At least, I don't know how much things you were available, and I understand, of
Yeah,
course,
yeah.
the implementation is CPython, it's not MicroPython. But because you were mentioning inspiration, might be also
Yeah.
useful.
Thank you for the tip. My answer is haven't tried it. I will need to look into it. It's a very good tip. Thank you. Okay then. Thank you again. Let's go to the party. Here.
Thank you for your speech. NDC team.
Thank you.